The last probability distribution I want us to take a look at, or discrete probability distribution, is the Poisson probability distribution. In a Poisson distribution, your events happen over a specified interval. So there's theoretically no limit to the amount of occurrences you can have other than the time limit that you have for your event. So examples of a Poisson distribution would maybe say fishing. The amount of fish caught in a day. While there may be some limits that, like how many fish are in that body of water you have, or maybe legal limits of what you're allowed to take, theoretically there's no real stopping for how many fish you could catch, especially if you think about the fact that if you're talking about for a day, there's no way you're going to catch the amount of fish, the total amount of fish, say in the ocean, by the time the day's out. So the time limit's going to hit long before any sort of technical limits. So we can view it as theoretically there's no limit to how many you could catch, other than our time limit. If we want to look at maybe crime rates, the amount of crime in a month for a city, again, theoretically there's no limit to how much crime could occur. So these are some examples of Poisson distributions, and the main way to recognize it is that we're looking at occurrences that happen over some sort of time interval, whether that time interval is a day, a month, a year, right? But we'll have some use of time involved. Now the occurrences must be random, independent of each other, and uniformly distributed over the interval. Basically, we want to have a nice consistent probability occurring. On the example of crime rates, especially for northern cities, it's normally kind of inaccurate to look at the probability over the course of a year, since crime rates tend to be there tends to be more crime during warmer months. In colder months, most people tend to stay inside, even criminals. So there's actually a decrease in crime normally in winter months, or at least for kind of the violent crimes, robberies, things of that nature. So we want the probability to kind of remain consistent throughout our time interval. Now there's some very nice properties with Poisson distributions. For instance, the standard deviation is equal to the square root of the mean. In other words, the mean and the variance are the same. Now the formula to find a Poisson distribution is mu to the x times e to the negative mu over x factorial. And I don't actually expect anyone to use this. Because Excel actually has a nice command. Similar to binom.dist, we have Poisson.dist. The difference is the inputs. You'll input x, mu, and then you can use your true or false, just like we did before. Usually you'll be using false, but if we need to find exactly a value, we could use true. So let's try it. For a recent period of 100 years, there were 93 major earthquakes. By major, we mean they measure at least a 6.0 on the Richter scale. Right. Now, we're told to assume that the Poisson distribution is a suitable model. So we know that the probability is going to remain consistent throughout our time interval. And our first question is to find the mean number of major earthquakes per year. So we're being asked to find our mean, and the key to find the mean is to actually pay close attention to the question. Earthquakes per year. Per is an indicator word for division. We had 93 earthquakes in 100 years. So our mean is going to be 0.93. For the second part, it wants us to find the probability of exactly 2 earthquakes per year in a randomly selected year, as well as the probability of more than 2 earthquakes. We'll show it here, and then we'll go and type it into Excel just so we can kind of see it all typed out. But using Excel, using our Poisson.dist, to find the probability of exactly 2, we can put in our Poisson.dist. We're going to put in our x, which is 2, our mean, which we found to be 0.93, and we want to use false for exactly. And we should get about 0.171. So let's turn to Excel. Since we're going to do exactly 2, we can go directly to Poisson.dist, put in our 2, This is going to ask for our mean, which we found to be 0.93. I'm on the wrong page. Hold just a second. There, that's better. All right, so our equals are Poisson.dist, 2. Our mean, which is 0.93. And then we're going to get that cumulative question. Well, in a lot of cases, you'll end up using true to do less than or more than. In this case, we want to use false because we want exactly 2. You can see we get about 0.171. Now the second part asks for more than 2, and this is where we're going to have to be a little bit careful, like we talked about in the binomial distribution commands. Anytime we talk about being more than something, we want to start with that 1 minus. And then we're going to put the first value we do not want. So for more than 2, it means we do want 3 and above. We don't want 2 or less. So we do not want 2 and everything below it. And since we don't want what's below it, we're going to use true instead of false. Usually about 0.068. The big key here is to recognize that we're using it the same way we did in our binomial distribution. We just have a different type of model that needs to be used because we're doing this over a time interval, not over a fixed number of trials like our binomial distribution. But the way we use the command is we use it the same way. So the more you get comfortable with the binomial distribution command, the easier the Poisson distribution command will be. Now, a unique thing about the Poisson distribution is that we can approximate the binomial distribution when our n is large enough and our probability is small enough. We normally say for it to be large enough, our n needs to be at least 100. And our n times p, to determine make sure our probability is small enough, n times p needs to be less than 10. So 10 or less. In the Illinois Pick 3 game, you pay 50 cents to select a sequence of 3 digits, such as 729. If you play this game once every day, find the probability of winning exactly once in 365 days. This is actually a binomial distribution. The two outcomes are win or lose, and we are playing a fixed number of trials. We're playing once every 365 days, so our fixed number of trials is 365. But in this situation, we can approximate with a Poisson distribution. Our n is greater than 100. Our n is 365. And then n times p. We just have to check n times p. Now the key there is to find p. So we need to find our probability of winning. Well, if you're selecting a sequence of 3 digits, don't forget to find the total number of ways we can do that. Turn the pen on. For our first digit, we have 10 choices. For the second one, we have 10 choices. And for the last one, we have 10 choices. For 1,000 possible sequences we could pick. So the probability of a win is going to be 1 out of those 1,000 chances. So our n times p will be 365 for n times 1 over 1,000 for about 4.365. Well, that's less than or equal to 10, so that's good. Both conditions for this problem are satisfied. We can actually, even though this is a binomial distribution, we can approximate it with a Poisson distribution. Now, we were asked to find the probability of winning exactly once in 365 days, so find the probability of it happening once is Poisson.dist. Our x would be 1. We found our mean, 0.365, because remember, mean is equal to n times p. And we want to use false because we're going to be looking for exactly 1. It'll come out to about 0.253. So let's switch to Excel real quick. Type that in just to see. So since we're going to do exactly 1, we don't need to worry about the 1 minus in front. We'll put in our 1. Our mean was that 0.365. And since we want exactly 1, we would use false. So we get about that 2.53. In the real world, the reason why we tend to prefer, why we would sometimes use a Poisson distribution to approximate a binomial distribution, is that because on the machine side, the calculations for a Poisson distribution tend to actually be a little bit simpler. So if we're going to have to do a couple million calculations, it can be a little bit easier or less labor to do it as a Poisson distribution instead of binomial. For your work, if you have a binomial distribution, but you're asked to use a Poisson, it'll be in your instructions. Otherwise, if you have a binomial distribution, you'll just be expected to solve it as a binomial distribution. If you have a Poisson, which you can recognize because it'll be over a time interval, of course you'll be expected to do it as a Poisson. But do read your instructions carefully. You might be asked to approximate a binomial as a Poisson.